Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be talking about molecular orbitals that are formed from your s and your p atomic orbitals. So let's get into this. So the first thing to talk about is that the fact that you can get molecular orbitals just like we added and subtracted the s orbitals on different atoms to form molecular orbitals, right? You can do the same thing with your p, d, and f orbitals on atoms. So you can take the atomic orbitals of your of the p orbitals on your different atoms, add those together, have those interact, and those can form molecular orbitals as well. So that's what we're going to talk about in this video. So since p, d, and f orbitals are not spherical, we're going to need to define a coordinate axis system. The Cartesian coordinate system is what we use for our p orbitals. So you'll remember that we have three p orbitals that are equal energy, and we label them according to what axis they are on. So either the x, y, or z. And so we have px, py, and pz. And the same goes for your d and f orbitals as well. But we're going to focus on the p orbitals since those are the simplest ones, apart from, next to the s orbital. So the s orbitals are spherical, but the p orbitals are not. They have like a dumbbell or clover shape, if you will. And so we need to identify them by what axis they are on. As with the ns, remember that n here just refers to the quantum number, the principal energy quantum number, the 1, 2, what energy level the electrons are at. So that that could be a 1 or a 2 or a 3. So you could have a 1s, a 2s, or a 3s. That's what the n stands for, and that's what it's going to stand for when we say np. So when we're referring to the p orbitals, it could be at an energy level 2 or 3 or 4 and so on. So as with the s orbitals, we can form molecular orbitals from the p orbitals or np orbitals by taking their mathematical sum or difference. We saw that in a previous video with the s orbitals. We're going to talk about that with regard to the p orbitals here in this video. So just like with the s orbitals, when two positive lobes are with the appropriate spatial orientation, right? Are they both along the x-axis? Are they both along the y-axis, right? So y cannot overlap or interact with z, and z can't overlap or interact with x because they're just not, they don't have the same orientation. So it's important that they have the same orientation, spatial orientation. So if they do have two positive lobes, right, if they're both positive lobes and they're in the same orientation along the z, for example, we'll talk about z here. If they're along the same z axis, it is the mathematical difference, not the mathematical sum. It's the mathematical difference of their wave functions that results in constructive interference, which in turn increases the electron probability density between the two atoms. We saw with the s orbital that the overlapping two positive wave function, it was the sum of their wave functions that led to constructive interference. In this case, it's the difference. Okay, so that's important to keep in mind. The difference corresponds to the molecular orbital called your sigma npz, right? This could be a sigma 2pz or a sigma 3pz orbital. And this is a bonding orbital, a bonding molecular orbital. And the reason it's called a sigma is because it is symmetrical about the internuclear axis. So in this case, we're talking about the z-axis. So in a nutshell, what we're talking about here is that, remember from before when we were talking about the overlap of the atomic s orbitals, right? The interaction to form a bonding orbital from the s orbitals, that resulted in a sigma because, again, the electron density was internuclear such that it formed a spherical or cylindrical shape such that it was along the internuclear axis. So when you have electron density, right, along the internuclear axis, that's going to be called sigma, right? So if it's bonding, it's going to increase the um, electron probability, right? So increasing the electron probability density between the two atoms, that's going to end up being a bonding orbital, and therefore it's going to be sigma because it's along that internuclear axis. And so here's a formula, right? So the sigma NPZ is equal to NPZ of the A. This is the atomic orbital of the atom A minus the NPZ of atom B. So these are the atomic orbitals. We're finding the difference, and that's going to give rise to the sigma NPZ molecular orbital, and it's bonding because there's no star there. Star would be antibonding. Okay, so now let's talk about the antibonding orbital due to the sum of these atomic orbitals. Okay, so let's talk about the other possible combination. The other possible combination of the two NPZ orbitals is the mathematical sum. So we just talked about the difference. Let's talk about the sum. When you sum them together, in this case, you're going to end up with a sigma NPZ star antibonding orbital. And so this is equal to NPZA, the NPZ orbital on one atom, atom A, plus the NPZ orbital on atom B. Those are going to be summed together, and that gives rise to an antibonding sigma orbital. So let me explain a little bit more. So in this combination, the positive lobe of on one NPZ orbital here is going to overlap with the negative lobe of the other, right? So again, we got before, when we were finding the difference, it was the positive overlapping with positive or negative overlapping with negative. We talk about positive usually more often. So when the two positive lobes overlap, that's going to lead to constructive interference and therefore a bonding orbital, in this case sigma. In this case, the combination of positive lobe with a negative lobe gives rise to the destructive interference that we talked about before. So two waves come together, they destructively interfere, means they kind of cancel each other out. And that's what happens here. So when you're talking about water waves, when they destructively interfere, they cancel out, and therefore you get no wave in a lot of respects. So they cancel out, and then you don't see a wave in the water at that particular juncture, right? When they constructively interfere, then they're going to build each other up, and you get a larger wave. So before, when we had constructive interference with the wave functions, right, positive with positive, you got a larger electron probability density between the nuclei. In this case, this is going to create an electron probability density node, which means zero probability, right? Just like when water waves destructively interfere, you're going to get no wave. Same thing here. The probability density is a node, meaning there's zero probability at that particular plane in space. So this is going to be between the two atoms. And so therefore we have an antibonding molecular orbital. Okay, so when you produce a node, you're going to get an antibonding molecular orbital. So again, because it is symmetrical, this orbital, even though you got the node there, this molecular orbital is symmetrical about the internuclear axis. And so because of that, it's going to be called a sigma orbital. And so sigma, again, refers to the fact that the electron density due to the molecular orbital is symmetrical around the internuclear axis, or about the internuclear axis between the two atoms. So that's what the sigma means. The star here is referring to the fact that this is an antibonding orbital, so we call it sigma NPZ star. And again, remember, the N is just the energy level, the principal energy level, so either a 2 or a 3 or a 4, depending on what atomic orbitals have overlapped with each other. So whenever atomic orbitals combine, we talked about this before, but I'll say it again. Whenever atomic orbitals combine, the bonding combination, if it's forming a bonding molecular orbital, the bonding combination is always lower in energy or more stable. So remember, lower in energy means stability. The amount of energy you have is related to stability. So the lower energy you have, the more stable you are. So this is always going to end up in a lower energy state, more stable than the atomic orbitals from which the molecular orbital came. And the anti-bonding combination is always going to be higher than the atomic orbitals, higher in energy or less stable than the atomic orbitals from which they came. Okay, now an important note here that I want to make is that this is kind of a little bit confusing because we're talking about the sum. In this case, the sum of the orbitals gives rise to the antibonding orbital, sigma orbital. Before, when we were doing the s atomic orbitals overlapping, it was the sum that gave rise to the sigma bonding orbital, and it was the difference that gave rise to the antibonding orbital. And so it's a little bit confusing. The thing you want to remember, though, is that the overlap of atomic orbital lobes with the same sign always produces a bonding molecular orbital. So it's the sign of the orbitals or the lobes that are overlapping that gives rise to either a bonding or antibonding. So if they're the same sign, right? If the orbital lobes are the same sign, that's going to produce a bonding molecular orbital, regardless of whether it corresponds to a sum or difference of the atomic orbitals. So don't bother yourself about trying to figure out, well, if this is a sum or a difference, how does that relate to antibonding or bonding? Pay more attention to the signs. If the signs are the same, then that produces a bonding molecular orbital, regardless of whether this is a plus or a minus. I hope that makes sense. Okay, so in the next thing I want to talk about and show you is the pictures or the drawings of what these orbitals look like, the anti-bonding and the bonding orbitals for the PZ. So stay tuned. Okay, so here we have some drawings of atomic orbitals and molecular orbitals. And so I want to kind of go over what I was saying before with regard to the antibonding and bonding molecular orbitals that are formed. And so we'll start with the bonding. So we have the bonding molecular orbitals, atomic orbitals on this side, and we have the molecular orbital that forms. And so you'll see here that the convention is that when you draw the lobes, it's always going to be for a linear molecule, which we're kind of assuming here. If you have a linear molecule, then the z-axis is along the internuclear axis of the molecule. So that's why I have the z-axis here. And then we always have the positive on the right, so it's going to be negative, positive, negative, positive. So the reason I'm pointing that out is because you might think, well, how did we get from the orange with the blue becoming orange in the middle, right? So orange is representing positive, blue is representing negative. I could flip this, but again, we're just drawing this according to convention. So on the right is the positive, on the left is the negative. So we have negative, positive, negative, positive. But for this one, we're taking the difference of the two atomic orbitals, and in this case, we are having an overlap of positive. So the positive is going to overlap with the positive, and that's going to form your molecular orbital here. So you can see here that the overlap creates a higher, electron probability density here in the middle along the axis. And So that is sigma. And then you've got the negative on this side here. So the negative lobes are on the outside here. And so this is a sigma NPZ bonding orbital. Because there's no node here, you have a high probability of finding the electron within that internuclear space. Okay, now for the anti-bonding orbital, you're going to have negative overlapping with positive, right? So the positive here will overlap with the negative here. And so again, this is where you are summing the atomic orbitals. So you're finding the difference here and you're finding the sum here. But again, when it comes to bonding and anti-bonding, it's not the difference or the sum that's really important. It's going to be the whether or not you're having positive lobes overlapping or positive and negative lobes overlapping. So here we're going to have a positive and negative lobe overlapping from the atomic orbitals. And so there you get this planar node here, this node along the plane where there is zero probability of finding the electron. And so you got this, again, it's going to be sigma because it's along, the electron density is along the internuclear axis, which is the z-axis, but you got this planal node here. And so this is the sigma NPZ star molecular orbital, an anti-bonding molecular orbital. And so this is what it looks like, what I was referring to before with regard to forming your molecular orbitals. Now, again, I want to point out this is two different ways in which the PZ orbitals can overlap. So remember, you have a PZ orbital on one atom and you have a PZ orbital on the other atom, and they're interacting with each other, and they can interact in two different ways. They can interact constructively or they can interact destructively. So this is the constructive interaction. This is the destructive interaction. And so when you have two atomic orbitals that interact with each other, you get two molecular orbitals, and these are the two molecular orbitals that form from the two p orbitals on the two atoms. And so that's it for the PZ, but we haven't really talked about PY and PX. So let's talk about those next. Okay, so here we have the orbitals, the px and py orbitals. So again, just like with the pz orbitals and the overlap with them, you have the exact same thing going on with the px and the py, just on different axes. So you'll see here that we got the z-axis and the x-axis here. And so the px orbitals are lined up on the x-axis. And so if you have the px on one atom and the px on another atom, if they add together, if you got positive and positive being summed together, right, that's going to lead to an overlap of electron probability density on the top as well as on the bottom of the plane of the YZ axis. So here it's going to be above. It's not internuclear. So we said before that with internuclear overlap, with internuclear electron density, that's what we're going to call sigma. But since we have the electron density above and below the axis, the internuclear axis, it's going to be a pi orbital. So here we have npx plus npx. This is going to give rise to a pi npx molecular orbital. It's a bonding orbital. Again, we don't have any nodes here, right? So you do have an overlap, and then you have an increased amount of electron probability density above and below, and it's no nodes there. So that's going to be a bonding orbital. And if you go over here, remember, you can overlap, you can constructively interfere. In this case, it's a summation of the orbitals. And if you can destructively interfere, so in this case, it's a difference. You're finding a difference between them. So, so in this case, you have, even though I have positive next to positive, it's just against by convention we have the positive on top. But if you have positive with a negative, that's going to destructively interfere, and then you get this molecular orbital here, and this is your pi NPX star bond. This is an anti-bonding molecular orbital. So you can see that there is a planal node where there's no electron probability density there. There's no probability, a zero probability of finding the electron there. So that's very different from what we have here. So notice that there's no node here. So this is a pi NPX star anti-bonding orbital. And again, you have the exact same thing with the py. So notice that the orbital here is on the y-axis. So the y-axis is coming in and out of the board, right? So perpendicular to the board. So again, the same thing. If you have positive adding to positive, if it's constructively interfering, then you'll get this cylindrical kind of electron probability density in the front and in the back. And so there'll be kind of a node in the middle on the z-axis. But here to the front and back, you've got this electron density, and again, that's going to be your pi NPY bonding orbital. So again, we have a bonding orbital for the px and the bonding orbital for the py interactions. And so again, you can have the anti-bonding interaction. So here it's a difference, and here you're going to have a positive with a negative. So again, for the purposes of convention, we have the positive kind of coming out of the board, the negative going in the board, but we're going to have an orange with a blue. So if we put those together, that's going to be destructive interference, and then you get this, and then you can see that there's a nodal plane going up and down on the x-axis here. So that would be the xy plane. And so because you had that node, that's going to be anti-bonding orbital as well. And I forgot to put that down. So this is going to be NPY, NPY, and this is going to be a pi star NPY. So there's the anti-bonding orbital. So these are the molecular orbitals that you get from the interactions of the p orbitals on different atoms forming molecular orbitals. So what does this look like in an orbital energy level diagram? Well, let me show you. Okay, ladies and gentlemen, so in this case here, we now have our orbital, molecular orbital energy level diagram. And so this is what it looks like for all of those molecular orbitals that I was showing you. So here, this applies universally to any any molecule that's made up of two atoms that are the same and that have p orbitals that have electrons in them, right? So if you have if you have a molecule that has the same atom and they're using p orbitals, then this would apply to them. If not, then it will look a bit different but similar. But we'll get to that later. So in this one here, you can see that you have the atom here. So if I write down here, we have the atomic orbital of A, right? So this would be, so let's say A atomic orbital. So that's going to be the first atom. Let's go ahead and use X instead of A because we're going to use A in a moment. So we have atom X, atomic orbital over here. We have atom X, atomic orbital over here. So they're the same atom. They have p orbitals available for combinations or overlap. And then we're going to form an X2 molecule with molecular orbitals. So as we saw, the pz orbital, if we're assuming, say, for example, a linear molecule, the pz orbital is going to overlap internuclearly. And so that's going to give rise to two molecular orbitals, a bonding molecular orbital, sigma NPZ, and an anti-bonding orbital, sigma NPC star. So you can see here that I'll talk about the energy level differences in a moment. And you'll see here that the NPY and NPY and NPX are going to interact, and you get the pi NPX and the pi NPY bonding orbitals here, and you get the pi NPX star and the pi NPY star orbitals here. And so we got two orbitals. So you can see that we got three atomic orbitals on this side. We have three on this side. That's a total of six. They combine together for a total of 6 molecular orbitals. Again, you get out what you put in. So whatever number of atomic orbitals you're adding together, you should get out the same number of molecular orbitals. And you see here that we got 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals, which makes sense because remember what I said before, if we are to fill all of these bonding and anti-bonding orbitals, molecular orbitals with electrons, the bonding order would be 0, right? So we saw that before with the sigma S and the sigma S star molecular orbitals. Okay. Oh, and with respect to that, remember our sigma S and sigma star orbital, molecular orbital energy level diagram where you had the sigma star, the sigma 1s star on top, the sigma 1s bonding orbital on the bottom. That would actually be down here below here. So since the p orbitals are higher in energy, then this is going to give rise to molecular orbitals that are also higher in energy. And so below here, you're going to have the 1s and the 1s star, the sigma 1s and the sigma 1s star molecular orbitals down here, but that's for later. Okay, so one other thing I want to point out is you'll notice that the sigma and the sigma star molecular orbitals have a greater energy difference compared to the pi and the pi star molecular orbitals. The reason for the large difference between these two relative to these two, or these 4 here, is because of the overlap between the lobes of the pz orbitals. And so because they're overlapping quite a bit in the internuclear axis between the atoms, that's got a much stronger overlap and interaction, and that's going to lead to a much larger difference in the energies. And you can see that the lowest energy is the sigma NPZ orbital, and you can see that here there's not as much of an overlap or interaction for the PY and the PX. We saw that with regard to our orbital pictures, you can see that the overlap is not along the axis, but outside the axis. So the overlap is not as great. The interaction is not as strong. And so the difference in energy between your NPX, your pi NPX, and your pi NPX star orbitals are not as large. And so that's how this is our orbital diagram for the NP orbitals that are involved in the molecular orbital formation of molecular orbitals. And that's it for this video. I hope you enjoyed this video. If you enjoyed this video, if this helped you in any way, if you learned a lot from this video or anything from this video, then please like the video, share the video, hit that notification or hit that like bell somewhere around here. Also, make sure that you subscribe to my channel. Help me out. Help me out here. Also, make sure that you hit that notification bell. When you do that, make sure you click all so you'll be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have any questions or problems that you need help with, or a topic you would like me to cover, put that down below. I'd be happy to do that for you. Thanks for joining me, and have a great day.